Now we're going to look a little bit more at wave optics and diffraction with different devices that we can use to create a diffraction pattern. So what is diffraction? It's basically, again, waves are coming through a slit and forming new waves. And we just looked at, in the last lesson, double slit diffraction, where we have the light coming through two different spaces and then interfering with each other. So Huygens principle is one thing that we can use to help understand what's going on, is that it requires the waves to spread out as they pass through the slits. So the spreading out of light is called diffraction, and diffraction occurs when waves pass through small openings and edges. We can also think of diffraction when it happens with just a single slit. The double slit is a little easier to think about because we have two different sources for the wave, but diffraction also occurs with just a single opening called single slit diffraction. You'll notice that the pattern looks very similar to a double slit diffraction. We have this wide central maxima. For the double slit, it's divided up into little bits because of the interference from the other slit. But here we have a very wide constant central maxima and then flanked by lighter maxima on either side. And what we'll find is that it's easier to measure where these dark areas are. So single slit diffraction equations are more focused on the dark areas than the bright areas. Whereas for single slit diffraction, it was pretty easy to get the center of those bright areas. So again, these are called maxima, and the dark areas are called minima. So the diffraction of a single slit depends on the width of the slit, and just like the distance between the two slits in double slit diffraction is important, the width of the slit is important. And as we get a narrower and narrower slit, we'll actually get a wider and wider band. So these are the slit widths. So a nice wide slit, we get a fairly narrow diffraction pattern, and with a tiny slit, we get a super wide diffraction pattern because it actually makes the wave spread out more. So another variation on this idea is Fraunhofer diffraction, where they put a lens in to amplify, to intensify the pattern. We're not going to really worry about that. We're not going to do any math with it, but it is another variation. So single slit diffraction, what's going on physically is that we have waves created as we go around the edges. So we have a wave created at each one of these points, and we're going to focus really on just 1 and 3 and look at what's going on. So according to Huygens principle, each portion of the slit acts as a source for waves. So we have really an infinite number of sources for waves. And the light from one portion of the slit can then interfere with the other portion of the slit as it comes around the corner. So we're looking at the middle one in particular because it's the distance over 2. So now mathematically, we have the same variables we did before, but now the d that was the distance between the slits is an a for the width of the slit. So all the waves originally in the slit are in phase because we have a coherent monochromatic light source. Wave 1 travels farther than wave 3 by an amount equal to the path difference. So this is the same delta we talked about. But now the path difference is a over 2 times the sine of theta instead of what we had for double slit diffraction, which was d sine of theta. So the path difference is exactly half the wavelength. When we have destructive interference, those two halves cancel each other out. So now we have the sine of theta dark is equal to m lambda a. And you notice that this is just m for destructive interference and not m over 2 because we've defined our delta, our slit, as being a over 2. But this doesn't give us any information about the variations in the intensity. So we know that this is a maxima, that the curve goes like this. We'd have to do more complicated mathematics to get that level of detail. So what happens is here we even see single slit diffraction on macroscopic objects such as this scissors handle. So the general features of the distribution are shown is that, again, we're going to be more concerned with the minima than the maxima for the case of single slit diffraction, but it's not a constant intensity. It certainly is a variable intensity. So we're going to try to pinpoint where the center of those dark areas are. Okay, so let's look at the math of this single slit diffraction. So in this problem we have light of wavelength 630 nanometers. That's our lambda is incident on a single slit with this width, so that's A, and positioned 2.4 meters from the slit, so that's our L. We want to determine the distance from the center of the bright central fringe to the second order minima on the one side, so that is going to be from the center to the second order. This would be m is equal to 1, m is equal to 2, and then we're going to find the distance between m is equal to 3 and m is equal to 4. So start out with the equation that we have derived thus far. So the first thing I want to do is find the angle, so theta dark to that second minima. So dark with m is equal to 2 is equal to the inverse sine of m lambda over a. So now I just put numbers in. Theta is equal to inverse sine of 2, because the problem said it's the second order, times 630 times 10 negative 9 meters. All over my slit width is 0.4 times 10 to the negative third meters. And that gives me a value of 0.180 degrees. So very small angle. We also know that tangent of theta is equal to y over L. So that's the opposite over the adjacent. And that gives me y, that distance, is equal to L tangent of theta. And putting numbers in, that's 2.0 meters times the tangent of that very small angle, 0.18 degrees. Gives me 0.0063 meters or 6.3 millimeters. Using the small angle approximation means that we basically have another variation of our formula, and that is y is equal to m lambda L over a, which we're going to use to solve the second part of the problem. But to start out with, we're going to look at that solution. So this is a nice typed up version of that solution. And if we use the small angle approximation, we can get the same exact solution because it is in fact a small angle. Okay, so now we're going to use this formula to figure out the distance between m is equal to 3 and m is equal to 4. So the difference between y is y at 4 minus y at 3. And so that gives us lambda L over a times m4 minus m3. This is just 1. So I just need to put the numbers in the first part. 630 times 10 to the negative 9th meters times my distance to my screen of 2 meters divided by my slit width, 0.4 times 10 to the negative 3rd meters. And that gives me 3.15 millimeters. Here's that nicely typed up again. And then now it's your turn to try to find the width. So here we have a slightly different wavelength. We're given the slit. So here is your lambda. Here is your A. And then how wide is the central maxima on a screen 20 centimeters away? Okay, hopefully you've gotten a chance to do all that. So we can either use this formula to find the theta, or we can go straight for the formula that we did before. The way I'm going to do it is I'm going to use this formula and work through it, but you can also use the formula that we've derived as well. So we got theta is equal to the inverse sine of, and so here we're trying to find the width of the first slit, so it's m is equal to 1 and m is equal to negative 1. So we're going to find half the width first and then just multiply it by 2. So 750 nanometers times 10 to the negative 9th divided by my slit width of 1 times 10 to the negative 6 meters. Those meters cancel, so that's a good thing. And then my angle is 48.5 degrees. So since my slit is so tiny, I'm actually getting a pretty big angle. So tangent of theta is equal to y over L. So y is equal to L times my tangent of my theta, so I get 0.2 centimeters, times the tangent of 48.5 degrees equals 0.227 meters. And remember, that's just from 0 to plus or minus 1. So to get the full width, we need to multiply that by 2. So here is that number multiplied by 2, and we get 45.3 centimeters.